Welcome to the Deep Dive, the show where we take complex topics, stack up the sources, and really pull out those nuggets of knowledge you need to be truly well-informed. Today, we're making a pretty fascinating leap. We're moving from the really mind-bending theory of quantum mechanics into the practical hands-on world. How do you actually program these weird machines? Our focus is the quantum coder, hands-on programming with Qiskit. So it's not just about understanding qubits and entanglement anymore. It's about making them dance. Okay, let's unpack this. Our mission today is really to demystify how you actually tell a quantum computer what to do. We'll explore how you get your quantum programming environment set up, dive deep into Qiskit's core workflow, the build, compile, run cycle for your quantum circuits. And we'll look at the visualization tools, which are super important for actually seeing what's going on in the quantum world. Crucially, we're also going to look at the difference between perfect simulations and, the real world, the results you get on actual hardware. That gives us a front row seat to the challenges and, the triumphs of this NISQ era, the noisy intermediate scale quantum era. Ultimately, you should walk away with a much clearer picture of the practical steps involved in becoming, potentially, a quantum coder yourself. So let's just jump right in. We've talked a lot about the abstract ideas before, superposition, entanglement, all that cool stuff, but how do we actually bridge that gap? From the elegant theory to, tangible action. How do we tell a quantum computer what we want it to do?
Well, what's fascinating here is that this transition, it happens directly through quantum programming. That's really where the abstract math, those descriptions of quantum states and gates, where they transform into code that can actually be executed. And one of the most powerful and honestly increasingly accessible tools for doing this is IBM's Qiskit.
Yeah.
It really lets you move beyond just drawing circuits on a whiteboard. You can actually write the instructions, build them, visualize them, and then run these circuits.
That feels like a really crucial step. Okay, so before we can even write that first line of code, we obviously need to set up our workspace, our environment. What are the main ways to get a Qiskit environment ready? And maybe more importantly, for people starting out, what's the recommended path?
Yeah, good question. You basically got two main routes you can take. First, for people who like having full control, you can set up a local environment right on your own computer. This means, installing Python, probably setting up a virtual environment, which is good practice anyway to keep projects separate. And then using pip, the Python package installer, to install the main Qiskit library and probably Qiskit visualization too for the plotting tools. It's pretty standard stuff if you've done Python development before.
Okay, the standard local setup. What's the other option?
The second option, and this is what I strongly recommend for beginners, is using IBM's cloud-based platform, specifically the IBM Quantum Lab. Think of it like a Google Colab, but for quantum. It's a free web-based Jupyter Notebook environment. And the key thing is Qiskit comes pre-installed. It's all set up.
Or no installation headaches.
Exactly. It's basically plug and play. You remove all that setup friction. And maybe the biggest plus is that it's already authenticated with your IBM Quantum account. Yeah. So you get this seamless access, not just to simulators, but to IBM's real quantum hardware right from your browser. Just log in and start coding.
Okay, that does sound like a dream, especially if you've ever wrestled with, dependencies and installations.
Yeah.
So let's say we're in the lab or we've got our local setup running. What's the basic workflow? You mentioned a kind of cycle for building a quantum program with Qiskit. What are those core steps?
Yeah, absolutely. At its heart, the whole process really simplifies down into three clear steps. Build, compile, and run. Build your quantum program, compile it for the target system, and then run it to get results. It kind of mirrors classical software development, but obviously with some very quantum-specific things to think about at each stage.
Build, compile, run. Got it. Let's break down build first then. When we talk about building, this quantum circuit object in Qiskit immediately comes up. What exactly is that? What does it represent?
The quantum circuit, that's really the absolute foundation. You could think of it like the sheet music for your quantum computation. It's the fundamental building block where you lay out all your quantum operations. So technically, it's a Python object that represents the actual quantum circuit diagram itself. It defines how many qubits you're going to use, and optionally how many classical bits you need those are for storing the measurement results later on. And then crucially, it holds the sequence of quantum gates that you apply to those qubits.
Sheet music. Or maybe a blueprint. I like that analogy. So you're designing the quantum algorithm step by step, gate by gate. Could you give us a quick, concrete example? Like, how would you build one?
Oh, definitely. Let's take the classic Bell state, right? The simplest example of entanglement. You start by creating a circuit. You need 2 qubits and let's say 2 classical bits to store the results. So you'd write something like QC quantum circuit 2, 2. Then you need to put the first qubit into superposition. You do that with a Hadamard gate, QCH0. The 0 means apply it to the first qubit, we count from 0. Next, you entangle them. You use a CNOT gate, a controlled knot. The first qubit is the control, the second is the target, QC.CNEZ01. And finally, you need to measure them to get a classical outcome. So QC.measure0101. That says measure qubit 0 and 1 and store the results in classical bit 0 and 1. And bam, that's your basic Bell state circuit built in Qiskit.
Right. Hadamard, CNOT, measure. Simple sequence, profound result. Okay, so we've built our circuit, designed our quantum dance. The next step you mentioned was compile. And this is where this term transpilation comes in. What exactly is transpilation and why is it so essential before running on real hardware?
Yeah, translation is super important, and it's a bit more than just simple compiling like in classical computing. It's really a sophisticated optimization and mapping process. Imagine you've written your perfect ideal quantum circuit, your sheet music. But the actual quantum computer, the hardware, it has limitations. It's like telling an orchestra to play your music, but maybe the violins can only play certain notes or the first trumpet can only interact with the trombone next to it.
Physical constraints.
Exactly. Real quantum chips have specific native gates they can perform reliably. Maybe they can do CNOTs, but only between certain pairs of qubits because of how they're physically wired together. This is called qubit connectivity.
Yeah.
So transpilation is like the quantum choreographer or maybe the conductor adapting the score. It takes your ideal circuit and rewrites it into a sequence of those native gates that the specific hardware chip can actually execute. It has to respect the connectivity, maybe insert swap gates if needed, and it also tries to optimize the circuit to make it shorter or less prone to errors. Qiskit's transpile function is essentially that intelligent quantum compiler doing all this heavy lifting.
Wow, okay. That really highlights the gap between the abstract math and the messy physical reality of building these things. So our circuit is built, it's been transpiled for specific hardware, now it's finally time for run. How do we actually, send this thing off to be executed and get the results back? And you mentioned these primitives earlier, like the sampler. What's that about?
Right. So historically, you might have used a lower level function called execute. But the modern approach in Qiskit, especially since version 1.0, really pushes towards using these things called primitives. Think of primitives as higher level interfaces. They kind of abstract away a lot of the boilerplate code and complexities involved in actually interacting with the backends, whether they're simulators or real hardware.
Makes it easier to focus on the algorithm itself.
Exactly. They streamline the whole process. You worry less about managing job submissions or parsing raw data formats. The sampler primitive is a perfect example, and probably the most common one to start with. Its job is pretty straightforward. You give it your quantum circuit or circuits, you tell it how many shots you want, that's how many times to repeat the execution measurement process. And what it gives you back is essentially the probability distribution of the measurement outcomes. It samples the output of the circuit.
So for our Bell state example.
For the Bell state, you'd run it through the sampler for, say, 1,000 shots. Ideally, you'd expect the results to show that the outcome SIPR2s occurred about 500 times, and 11 occurred about 500 times. The sampler gives you back these probabilities, or quasi-probabilities, telling you the likelihood of observing each possible classical bit string.
Got it. Sampling the output probabilities. Okay, now this is where I think it gets really interesting, because the quantum world is just so counterintuitive. Visualization feels absolutely key. How can we actually see the quantum circuit we've built? What tools does Qiskit offer to visualize that blueprint we created?
You're absolutely right. Visualization is critical. And Qiskit makes it pretty easy. For a really quick look, maybe in a terminal, you can just do qc.draw. It gives you a simple text-based representation. It's functional,
Like ASCII art for quantum circuits.
Kind of, yeah. But for something much nicer, especially if you're working in a Jupyter notebook, which is very common, you want to use qc.draw style emble. The emble stands for matplotlib, the standard Python plotting library. This generates a much richer graphical diagram. You see the horizontal lines for qubits, the double lines for classical bits, and then the symbols for each gate placed nicely in sequence. It looks like the diagrams you see in textbooks or papers. It really helps understand the structure.
That sounds incredibly useful, yeah, for debugging or just explaining what you've done. Now, when you're using a simulator, you mentioned this unique advantage, something you can't do on real hardware, which is peeking at the quantum state itself before measurement. What tools does Qiskit give us to visualize that underlying state vector, to really understand what the quantum state is at different points?
Yeah, this ability to inspect the state vector on a simulator is It's like having quantum X-ray vision. It's invaluable for learning and debugging. Qiskit provides some really cool tools for this. One is plot staticity. It creates this 3D bar chart. The floor represents all the possible basis gates, like 0 to 1, 10, 11 for 2 qubits. And then bars, or cities, rise up from the floor. The height of the bar corresponds to the probability of measuring that state, and it uses color and potentially another axis to show the phase information, the real and imaginary parts of the amplitudes.
So for the Bell state, what would that look like?
For the Bell state, first chord 2 plus first chord, you'd see 2 equal height cities rising from the Fusnot 11 positions on the floor and basically flat ground everywhere else for 0, 1, and 10. It visually shows you the superposition.
Okay, that's one way. Are there others?
Another really insightful one is plot block multivector. The block sphere is usually used to represent the state of a single qubit. This function plots each individual qubit from your multi-qubit circuit on its own block sphere. Now, what's really neat is what happens with entangled states, like our Bell state. If you try to plot the state of just the first qubit or just the second qubit on its block sphere,
What do you see?
you see a vector pointing right to the center of the sphere. This represents a maximally mixed state. It visually tells you that the state of that single qubit is undefined on its own. Its state is perfectly correlated with the other qubit, but individually, it holds no definite information until measurement. It's a powerful visual demonstration of entanglement. The state is in the correlations, not in the individual parts.
Wow, that's a profound way to see something so abstract. Okay, so we visualized the circuit, maybe peeked at the state vector on a simulator. Now, after we've actually run the experiment, used the sampler, got our shots back, what's the main go-to visualization for understanding the results, the outcomes, and what does it show us?
The single most important plot after running an experiment, hands down, is the plothistogram function. You feed it the results object you get back from the sampler or other execution methods, and it generates a simple bar chart. The horizontal axis shows all the possible classical outcomes you could have measured, like 0, 1, 10, 11. The vertical axis shows how many times out of all your shots each specific outcome was actually observed.
So it's just counting the results.
Exactly. It's a frequency count. For our ideal Bell state experiment with 1,000 shots, the histogram would ideally show a tall bar at 0 reaching up to about 500, another tall bar at 11, also around 500, and then crucially, no bars, or maybe tiny ones due to simulation noise, at 0, 1, and 10. It's your direct feedback. Did the experiment yield the expected distribution? This plot tells you immediately.
Makes perfect sense. So we've touched on simulators letting us test things ideally. What's their overall role? Why are they so crucial? And what's the main tool in Qiskit for simulation?
Simulators are absolutely essential, especially now in the un-IceQ era. Their main role is to provide a perfect, controllable, noise-free environment. This lets you do a few critical things. First, you can verify the logic of your quantum algorithm. Does it mathematically do what you intend it to do, assuming perfect quantum operations? Second, you can determine the ideal output distribution you should expect. This gives you a baseline to compare against when you later run on noisy hardware. And third, because they run locally or on powerful classical machines, they're often much faster for developing and debugging than waiting in queues for real quantum hardware. The primary tool for this in the Qiskit ecosystem is the Air Simulator. It comes from the Qiskiteer package, which is designed for high-performance simulation. It's fast, it's versatile, it can simulate different noise models too if you want, but its default is that perfect ideal simulation.
Okay, indispensable for development and benchmarking. But of course, the ultimate goal for many researchers and developers is to run their algorithms on real quantum hardware. How do you actually take that same Qiskit code, the quantum circuit you built, and run it not on your simulator, but on an actual quantum computer, like one of the IBM quantum systems available through the cloud?
And this is where the design of Qiskit, especially with the primitives, really shines. The transition is designed to be remarkably smooth. Assuming you're using, say, the IBM Quantum Lab, you're already authenticated. If you're local, you'd first need to save your IBM Quantum API token once using a command like ibmprovider.saveaccount. Then, instead of getting the Air Simulator backend, you connect to the IBM provider and ask it for a list of available real hardware backends. You might see names like in Brisbane or IBM Kyoto.
So you choose a specific machine.
Right, you choose one that's online and available, maybe one with enough qubits for your circuit, using something like provider.getBackend, IBM Brisbane. And here's the key part. Instead of creating a sampler that uses the Air Simulator, you create an IBM sampler instance and you tell it to use the real hardware backend you just selected. From that point on, the code to run the job using sampler.run circuit shots. Looks essentially identical to how you ran it on the simulator.
Wow, so the primitive abstracts away whether it's talking to a local simulator or a real quantum computer halfway around the world.
Pretty much. That's the goal. The main practical difference you'll notice is that when you submit the job to real hardware, it goes into a queue. So retrieving the results isn't instantaneous like on a simulator. It might take minutes or sometimes longer depending on how busy the system is.
Yep.
But the coding pattern remains very consistent.
That's really powerful. Okay, this brings us to maybe the most crucial learning point. You run your Bell State circuit on the perfect air simulator. You get that nice histogram with basically just 0, 0 to 11. Then you run the exact same code, just pointing the IBM sampler to in Brisbane, wait for the results, and plot the histogram again. And it looks different. You see those bars for 0 and 11, maybe a bit lower than 50%, and now you see small, but definitely non-zero, bars appearing for 0, 1, and 10. What does this difference, this discrepancy, teach us? What's going on?
Yes. If we connect this to the bigger picture, that moment of comparing the two histograms, the perfect simulation versus the real hardware result, is probably one of the most powerful and immediate lessons in quantum computing today. Seeing those unexpected 0 on 1 and 10 counts pop up isn't because you made a mistake in your code.
It's noise.
It's quantum noise, exactly. It's the signature of the NISQ era noisy intermediate scale quantum. Today's quantum processors are incredible feats of engineering, but they're not perfect. Qubits lose their delicate quantum states over time due to interactions with their environment. This is called decoherence. And the quantum gates, the operations we apply, they aren't perfectly precise. There are tiny errors in rotation angles or timings. These are gate errors. All these imperfections accumulate during the computation, causing the final state to deviate from the ideal one. So when you measure, you sometimes get outcomes that should have zero probability.
So comparing the simulator and the real results gives you a direct measure of the hardware's imperfection.
Precisely. It gives you a first-hand, very tangible understanding of the primary challenges that physicists and engineers are wrestling with right now. How do we build better qubits? How do we perform gates more accurately? How do we develop error mitigation techniques to reduce the impact of this noise, even if we can't eliminate it completely yet? That comparison is a powerful lesson in the realities of current quantum hardware.
That really crystallizes the state of play. Okay, so to wrap up this deep dive then, if someone goes through this process, learns the theory, sets up Qiskit, builds, transpiles, runs on simulators and real hardware, uses the visualizations, what are the core skills, the key takeaways, the main lessons learned from making that journey from quantum theory to hands-on Qiskit programming?
I think the biggest takeaway is that this journey really transforms quantum computing. It stops being just this abstract, almost mystical science, and it becomes an accessible, practical, hands-on engineering discipline. The core skill set you come away with is mastering that fundamental workflow, using quantum circuit to translate your quantum ideas into concrete code, understanding the absolute necessity of transpile to bridge the gap between that ideal code and the constraints of real physical hardware,
Right.
and then using the modern primitives, like the sampler, to efficiently execute those programs and get meaningful results, whether simulated or real.
And the visualization tools seem critical too.
Absolutely. A huge lesson is appreciating the power of visualization. Tools like plothistogram, plasticity, plot block multivector, they aren't just eye candy. They are essential for building intuition, for debugging, for truly connecting the lines of code to the underlying, often weird quantum phenomena you're manipulating. And perhaps the most impactful lesson, as we just discussed, comes from that experience of seamlessly switching between the perfect simulator world and the noisy real hardware world. It gives you undeniable direct insight into both the incredible promise of what quantum computers might achieve and the very real, tangible challenges of this current NISQ era that we need to overcome. It's really a hands-on way to become part of shaping that future.
So what does this all mean for you listening? It means you've just explored the actual practical steps involved in programming a quantum computer. You're talking about manipulating qubits, creating entanglement, and seeing the results, maybe not with your own eyes directly, but through the data, through these visualizations. It shifts from just theory to something tangible, something executable, a real step towards a future potentially powered by quantum computation. And here's a final thought to maybe chew on. Consider how learning these hands-on steps, working with Qiskit, grappling with noise, it isn't just about understanding the current challenges. It's actively building the foundational skills, the practical know-how that will be needed to overcome these challenges, to build better quantum computers and algorithms, and ultimately to shape the technological landscape of the future. You're not just learning about quantum computing, you're learning how to build it. Thank you so much for joining us on this deep dive into quantum programming with Qiskit. If you found this valuable and you want to keep exploring the absolute cutting edge of technology, definitely be sure to subscribe to our channel. tech, AI, and beyond. We'll be back very soon with another deep dive.